So the aim of this presentation is to explore and explain the trends in melting points as we move across period 3 of the periodic table. So on this table, going from sodium down to argon corresponds to going across period 3 on the periodic table. And hopefully in this column you can see that there's various different numbers and no obvious trend left to right. So let's have a look at these different elements. What I'd like to consider is these 3 elements together. Those are the metals. Silicon on its own up here, and these 4 non-metals together as well. So let's begin by thinking about the 3 metals together over here. So sodium, magnesium and aluminium. As metals, of course, they experience metallic bonding, and therefore they have giant metallic structure, which corresponds to a lattice of layers of positively charged metal ions surrounded by a sea of delocalized electrons. And of course, it's the very strong electrostatic forces of attraction between those metal ions and the sea of delocalized electrons, which dictates the amount of energy needed to separate those atoms apart from one another, and therefore dictates the melting point of the metal. So if we consider Na, the metal ions in question are Na plus ions, magnesium Mg2 plus ions, and aluminium Al3 plus ions. So in general, the Na single plus ions will attract those electrons less strongly than the Mg2 plus ions would in their lattice, which attract a little less strongly than the Al3 plus ions in their lattice. You can see that this is not a linear trend between those 3. It might be surprising that aluminium has such a similar melting point to magnesium. And in actual fact, the melting points of metals are quite challenging to explain thoroughly because they depend partly on the charges but also partly on the shapes and the distances between those ions in those lattices. That way exceeds A-level requirements, but by all means go and have a read of that if you're interested in that. So for these 3 elements, metallic bonding with giant metallic structure, the strength of the electrostatic forces of attraction between the ions and the delocalized electrons is what dictates that melting point. Now let's have a little look at silicon here on its own. Now silicon is macromolecular, which means it's got a giant covalent lattice structure. So all atoms are joined by very strong covalent bonds. Now that means then that to separate those atoms within that lattice, it's important to supply a huge amount of energy in order to break those very strong covalent bonds. And it's for that reason that silicon itself has got such a high melting point. Let's now consider those 4 nonmetals. So the 4 nonmetals, P4, S8, Cl2 and Ar. Well, these 3, P4, Cl2 and S8, are all molecular substances, whereas argon just exists as a monatomic substance. It's a monatomic gas, so that means it just exists as isolated argon atoms. But in each of these cases, what dictates the boiling point is the strength of the intermolecular forces of attraction, or indeed interatomic forces of attraction if we're talking about the argon. So in these examples, weak forces of attraction between molecules, or if it was argon, just the atoms, require little energy to be broken. Now, if you imagine in this example here, what's important, let me just neaten that up a bit, to be broken, there we go. What's important about this is the fact that each of these substances is completely nonpolar. And so those weak forces of attraction are in fact van der Waals forces of attraction. And the van der Waals forces of attraction will depend in strength on the number of electrons present. So the strength of the van der Waals forces of attraction depends on the size of the molecule, the MR of the molecule, but primarily because larger molecules have more electrons, and therefore the instantaneous dipole-induced dipole attraction becomes stronger. So S8 has got bigger molecules than P4, and P4 has got bigger molecules than Cl2, and Cl2 is bigger than Ar. And so in terms of the strength of those van der Waals forces of attraction, S8 has the strongest forces, then P4, then Cl2, and then Ar, because S8 has got the strongest van der Waals attractions between the molecules, whereas Ar has got the weakest van der Waals forces of attractions between its atoms because there are fewer electrons present.